In this lecture, we will use the SPI simulator to analyze the behavior of a Class A amplifier. We will compare the results that we will find here with the theoretical calculations that we run during the lectures. The circuit that is shown here is quite simple and it has been studied before. We can be fast in analyzing this one. This is the input signal, that is 12.5 volts sinusoidal waveform at 1 kHz. This is a bias resistor. This is the active device. This is the bias current generator of 0.5 amps for 500 milliamps. This is the load resistor, 25 ohms, and the circuit is biased with a positive 12.5 volt voltage source and a negative minus 12.5 volts voltage source. Hence, we have a total voltage of 25 volts for this circuit and around half amp of current. The active device is an NPN bipolar junction transistor, but as you can see here, this is not a generic transistor. We choose a particular model of transistor from the list of devices that we have in this simulator. The one that has been selected is a transistor that has a maximum voltage, we will study this later, VCE, or that is 30 volts, and the maximum current of 7 amps. So current and voltage are larger than what is expected in this circuit with a quite good safety margin. It will be also necessary to calculate the power and to study which is the best device from the power dissipation and cooling point of view, but this has not been done here. In this simulation, we can analyze the input and the output voltages. Let's run the simulation and see what happens. This is the results of the simulation. The result of the simulation, the top plot shows in light green the input voltage, a sinusoidal waveform 12.5 maximum voltage, and a dark green waveform that is the output voltage. As you can see, they are similar, even if the output voltage is slightly smaller because there are some non-linearities involved in the large signal amplification that we are asking to this active device. The circuit is then working properly, but we can also analyze which is its efficiency. The bottom plot here shows in red the instantaneous power dissipation taken from the voltage sources. It is calculated as the sum of the power dissipated by both voltage sources, and it has a sinusoidal shape, as you see here. The average value is around 12 watts, more or less. The blue waveform instead shows the power provided to the load, calculated as the multiplication of the voltage on the output and current on the output resistor. This curve is also sinusoidal, as you can see, and you can also see that the average value is much smaller than the average value of the red curve. This tells us that the efficiency cannot be very large. If we want to calculate better these waveforms, this efficiency and these power dissipations, we can also ask to the simulator to measure them for us, including proper directives on the simulation, and these directives indicate which measurements to extract from the waveforms. These directives that we included in this simulation ask to the simulator to calculate for the given waveforms the average of this power dissipation, power taking from the source, we call it PS, and this is the power that we want to calculate. The average of the power provided to the load, the average of the power dissipated on the active device, and the efficiency. These average values are exactly what we need because we are running a simulation that is an entire number of periods for the input signal, and this means that this average is exactly the average power that we expect. Running this simulation, we can see which are the values calculated using the menu view spice error log, and on top here you can see we will have the PS that is around 12 watts, the PL that is around 2.4 watts, and the power dissipated on the active device that is 4.4 watts more or less. The efficiency is just 19%, let's say 20%. That is smaller than what we expect from the theoretical point of view because the output voltage is smaller than the input voltage, and also because the maximum theoretical value is just an ideal value that in principle cannot be reached. And also this simulation shows that the efficiency is, as expected, quite low. We can change the amplitude of the input signal in order to see which is the effect on the efficiency and on the waveforms. We can try to increase it, let's say 25 volts, but this will cause very big non-linearities on the output. You can see here that the input voltage is sinusoid, but the output voltage is clamped at 0 and at minus 12 volts and plus 12 volts, and this is not a valid working situation. It's also not the case to calculate the efficiency here. Probably the maximum value that we can use is around 12.5. Let's see with 15 volts what happens. You can see you have a clamping here, and probably also 13 will give us a clamp on the output. Barely no clamping here, we are very close to the maximum. In this case the efficiency is 21%. We can also reduce the amplitude of the input signal, let's say 5 volts, and in this case you can see that the efficiency is even worse, just 3%, and the power dissipated on the active device is increasing, now 6 watts. The worst case that we can have is when the input signal is nil, and we do expect that 0 power is provided to the load, to the output, to the load. This is 0, and the power dissipated on the active device is more or less 50% of the power taken from the source. 7 watts against 12.4 watts. The efficiency is nil, obviously. This simulation has shown you how to use the simulator to study the behavior of the circuit, but also to study and measure the power dissipated and taken from the various sources, and how to measure the efficiency of the circuit.